This video is specifically for students in periods 4 and period 6. I'm going to cover the pieces because of the shorter All Saints Day Mass schedule that we had today. I'm just going to cover some of the ending pieces from the section 4.3 lecture. For those of you who are in period 6, watch the whole video. For those of you who are in period 4, you've already seen everything that's on this page. And so just look for the start where I start working in this. I'll just go ahead and look for where you see an asterisk next to graphing practice. And that'll be the part of the video that you can start to watch. So after we covered our basics on logarithms, the inverse of exponential functions, we talked about how to rewrite equations, some of the basic characteristics of logarithms at a simple level. We're now going to talk about graphing them. We already had graphed log base 2 of x on our prior page. That was the first function that we built, the first logarithmic function we built, which happened to be the inverse of y equals 2 to the x. So here on this graph, you were given two others on this page, two other exponential functions, y equals e to the x, y equals 10 to the x. And they've been graphed. You see their normal characteristics, and they have then been flipped over the line y equals x to build their inverse, which happens to be two more logarithmic functions, log base e of x, also known as ln of x, log of x, also known as log base 10 of x. And every logarithmic function is going to have this type of shape. The basic logarithm, called a parent logarithm, log base b of x, will have this type of shape. Placement of points will be different depending on what the base is, but the general structure and shape is going to be the same. Now on the graph, there's a couple things that are just missing that I'm going to go ahead and fill in very quickly. Just showing some end behavior. And also what we talked about with our earlier graph, but what we'll reiterate here, I've already gone ahead and done it. You'll notice that I've added a vertical asymptote at x equals 0 for both of my logarithmic functions. So we got a basic shape. Let's now talk about characteristics. Just like we talked about characteristics of exponential parent functions, we're going to do the same for logarithmic parent functions. First things first, these logarithmic functions pass the vertical and horizontal line test. They are one-to-one functions. The domain of a logarithmic function is 0 to infinity, not including 0. Leads to an important point that we'll talk about in a moment. The range, if we follow our end behaviors, happens to be negative infinity to positive infinity. Hopefully not too much of a surprise, because this is the exact flip-flop of the domain and range that you would happen to see for an exponential function that we talked about in our last class. Every logarithmic parent function has the point 1, 0. It's kind of your freebie. It's the point that will always be there. Just as we said on an exponential function, 0, 1 will always be present. On a logarithmic function, 1, 0 will always be present. And again, we talked about a vertical asymptote at x equals 0. Now there's one other thing I'd like to add to this, and that is you always will have the point b, 1 on your logarithm graph as well. So log base b of x, you can always be guaranteed that you'll have the point b, 1 on the graph. Extra, as I said, a freebie, a free point. Now, there's a couple important takeaways. The domain of a logarithmic function is 0 to infinity, not including 0. In other words, it's all values greater than 0. It leads to an important statement. You can only take the logarithm of a positive number. You can only take the logarithm of a positive number. You can't take the log of 0. You can't take the log of a negative number. Very important point. And you can see it just by looking at the graph. The domain, the inputs that you can put into the logarithmic function have to be greater than 0. And another point is, when we take our parent logarithmic function with the vertical asymptote at x equals 0, any horizontal shift that we have of the parent is going to take the vertical asymptote with it. Just like the horizontal asymptote of an exponential function moved with a vertical shift, the vertical asymptote of a logarithmic function will move with a horizontal shift. Very, very, again, important point to take. So that's our fundamentals of graphing logarithmic function. We're going to move into graphing practice now. So this is the part where section 4 can join in. We're going to be asked to graph the function log base 3 of x plus 2 plus 5. And we're going to build it off of the parent function y equals log base 3 of x. Now, I'd like you to do a little bit of housekeeping with this graph. There was a couple formatting errors that we had here. Number one, I'm going to want you to include the word range over here in your box because we're going to want to define the range and domain of this transform function. The second thing I'd like you to do, our x-axis is too low. So what I'd like you to do is just move up a couple spots and make this your x-axis. So just put your true x-axis right here. And I'm going to write over here y equals 0 just so you can see it. All right. Now, here's what we're going to do. We're going to graph the parent function y equals log base 3 of x. I'm going to do that in red. And I'm going to use a little bit of a helper. Remember way back when I said make sure you understand how to do the table y equals 2 to the x, y equals e to the x, y equals 3 to the x. We're going to use these points by flip-flopping them. We get a very simple method of points that are associated with log base 3 of x. And so we're going to take them. Remember I said 1, 0 is always there. There's 1, 0. I said 3, 1, 2, 3. Our next point is 9, 2, which is pretty far out. It's going to be a little bit off the graph. Somewhere about like right there. And so I can start my curve. So I'm going to also say y equals log base 3 of x is going to be in red. And then the rest of my function just kind of will plummet down like this. And I would have my good old vertical asymptote at at x equals 0. So there's a parent function graphed pretty quickly, pretty simply, got the right shape. What are the transformations to go from log base 3 of x to log base 3 of x plus 2 plus 5? Well, there's a couple. The x plus 2 is done before you evaluate the logarithm. That's a quote inside the function. That means a horizontal shift left 2. And the plus 5 outside after I do all the logarithm work, that's a vertical shift up 5. Now, what's important to note? We talked about vertical asymptote follows the horizontal shift. So my vertical asymptote must shift left 2. What's that mean? Well, it used to be right here at x equals 0. When I shift left 2, my new vertical asymptote is going to be at x equals negative 2. X equals negative 2. So that kind of helps me. I know this part of the graph is now going to start dying over here to a certain extent. But let's do a little bit more work. Let's start taking, we have a few points to really work with, but let's go ahead and mention them. I'm going to come back over here for a second and use my table. I said I need to do what? I need to shift left 2 up 5. So 1, 0 is going to become negative 1, 5. Shift left 2 up 5. 3, 1 is going to become 1, 6. 2 to the left puts me back at x equals 1. 5 up, y equals 6. And then that point 9, 2, well, now at least I left 2 and up 5. It's going to put me at 7, 7. So I'm going to take these points. Again, here was my 9, 2. I'll let my arrow just kind of continue off past this point, 9, 2. Let's go ahead and transform each of them and hit the points that we talked about. I said negative 1, 5. Negative 1, 1, 2, 3, 4, 5. So there's this point transformed. What am I going to have next? I'm going to have my point 3, 1. I'm going to move it over 2. 1, 2. And move it up 5. 1, 2, 3, 4, 5. And my point 9, 2. What am I going to do with that? Well, I'm going to go ahead and Do the same thing. Move to 7, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And the rest of my graph just is going to move smoothly down this way. So that's how to work the transforms. Let's talk about a couple more pieces. What's the range of my new function? It's all real numbers. What's the domain of my function? Well, with that asymptote now at x equals -2, my domain becomes -2 to infinity. So I'm going to hold on. You can pause this video for a second. I need to get a battery to charge in so we don't lose the rest of the video. This will continue in a couple moments, so just bear with me. So apologies for that, but let's keep going now. And we're going to cover the last page, only working with two examples, the last example and the first example on the last page of the notes. Now, we said before that you can only take the logarithm of a positive number. Well, what's the opposite of that? You cannot take the log of a number that is less than and equal to 0. Got to be greater than 0. So if your number is less than or equal to 0, you cannot take a logarithm. So in these questions, we have transformed logarithm statements, and we're going to be asked to find the domain. What can we take the log of? Well, remember, you can only take the log of a positive number. So in this case, we're trying to take the log of what? 2x minus 3. We need that to be positive. And that translates into 2x minus 3 has to be bigger than 0. Well, we can solve this pretty simply algebraically. 2x is greater than 3, and x is greater than 3/2. That's all we need. So anytime we put a value of x that's bigger than 3/2, we know that 2x minus 3 is going to be a positive number. We can take the logarithm. If we put something equal to 3/2, gee, we'd be taking 2 times 3/2, 3 minus 3, we'd be asking ourselves to take the log of 0. You can't do that. The log of 0 doesn't exist. So we can only take values greater than 3/2, which translates in interval notation to a domain of 3/2 to infinity. The ln of absolute value of x minus 2. Okay, well, just like before, we need the absolute value of x minus 2 to be greater than 0. Now we can do a couple things. We can talk about it from a graphical standpoint, which we will in a moment, but let's do something else. Remember, the absolute value takes what? Whatever's in there and makes it positive. So any number that comes in here should be, quote, positive. If it's a negative number, fine, it'll turn it into a positive. If it's a positive number, it'll stay positive. The only value that could get us in trouble is, well, what? If you try to take the absolute value of 0, because the absolute value of 0 is 0, and the last time I looked, 0 isn't greater than 0. So what we're finding is, hey, you know, the absolute value of x minus 2 from an algebraic standpoint is going to be great as long as x is not equal to 2. A value less, fine. It'll become a negative number that'll turn in positive. Hey, if it's bigger than 2, so what? We'll have a positive number. It'll stay positive and will be bigger than 0. So the only thing we can't have is x not equal to, the only value that we can't have is x equal to 2. How do we write x not equal to 2 in interval notation? Negative infinity to 2, union 2 to infinity. Now, one other way to look at this is, hey, let's do the graph of absolute value of x minus 2. Well, it looks like the v shape, the absolute value function, shifted over to the right by 2. 1, 2. There we are. Now, graphically, I could look at this, and that is x minus 2. Well, gee whiz. X minus 2 is positive everywhere, except for when it is equal to 0. There's a spot where the absolute value of x minus 2 is equal to 0. But what's that turn out to be? It's at 2. The same thing that we talked ourselves through over here is the same thing that we see here visually. The only spot where we would get in trouble because we'd be asking ourselves to take the ln of 0 is when x equals 2. What's that telling us? All real numbers except x not equal to 2. And again, come back to our same interval notation. Negative infinity to 2, union 2 to infinity. So this is the fundamentals of working with logarithms, some basic pieces on domain, the keys on rewriting, going from exponential to logarithmic and vice versa, the solving of basic logarithmic statements, and basic graphing of logarithmic functions, knowing their key characteristics, and being able to identify transformed logarithmic graphs, with the final piece of remembering from our graphs that the domain of a parent logarithmic function has to be 0 to infinity, not including 0. We can only take the log of a positive number, and that'll trigger our understanding of functions that we can take a logarithm with and functions in spots where we cannot take a logarithm.